In this recording, we're going to continue to work with polynomial identities. Specifically, we're going to start out making a connection to the Pythagorean theorem. So in exercise 4, it says that a right triangle has these side lengths, 2x and x squared minus 1 and x squared plus 1. And what we're going to try to show is that this creates a true statement. Okay, so in other words, a squared plus b squared equals c squared. We can see it from the graph, but we can't just, or from the drawing, we can't just trust that it's going to work for those particular values. So we're going to work out the algebra on both sides and show that both sides are equivalent. So in this case, I'm going to work on the left side, all right? And I'm going to write these out twice. Okay, so I've worked out the left side. I've simplified it the best I can. Now what I need to do is simplify the right side. So again, I'm going to write it twice. Okay, I'm going to distribute this out. And lo and behold, it is the same. X squared, x to the fourth, plus 2x squared, plus 1. So we've shown that as long as x is greater than 1, these two sides are equal for any value of x. All right, so based on that, we can explain why any even integer must be part of the Pythagorean triple. So take a moment to make sense out of that. Why any even integer would have to be a side here. Think on it. Play the recording when you're ready. Okay, so I hope you took time to consider this and you realized that I don't know too much about x squared plus 1 or x squared minus 1, but certainly 2x has to be an even integer, right? Because if x is an integer, 2x would be an even integer, right? And of course, we're not talking about negative numbers as they relate to triples or sides of triangles. So it says, explain that, and we can write it out in words. Okay. Any even integer could be represented by the side that is 2x. So if we were to show that it works for a triple that has 10 in it and another one that has 14 in it, what would you let x be if your side is going to be 10? And then therefore the other two sides, but you think on that. Okay, so you said, well, if x is equal to 5, then 2x equals 10, right, subbing in the 5, and x squared plus 1 would be 25 plus 1, subbing in the 5, 26, and subbing in the 5 here, x squared minus 1, that would be 25 minus 1, that would be 24. So we'd have the Pythagorean triples of 10, 26, 24, or change the order. Okay, so I want you to do something similar with a side that has 14 in it. And play the recording when you're ready. Okay, so hopefully you considered if x were to be equal to 7, 2x would equal 14. And therefore, if x is 7, x squared plus 1, squaring the 7, 49 plus 1, that would be a 50. And x squared minus 1 would be the remaining side, so square the 7 minus 1, that would be a 48. So the numbers 14, 48, and 50 that makes a Pythagorean triple. And you should test that out with your calculator. Do 14 squared plus 48 squared and see if it's equal to 50 squared. It should check out. Pretty cool stuff. All right, for our last example, this gets into the expansion of binomial expansion, a plus b to the third power. And it turns out it works out to be this. And this is something we'll look at down the road, where this is actually something that relates to Pascal's triangle. And there's a lot of patterns that are involved with the coefficients as well as the exponents here, the variables. But we don't know that yet, so let's just work on this identity. Let's expand the left side and show that's equal to the right side using algebra. So we'll leave the left-hand side, we'll leave the right-hand side alone. Okay. I want you to take your time to expand this. Multiply two of them, and they get your answer. Multiply the third one by the product of the first two. And you'll know if you're right. You'll know if it's equal to that right side. It's not cheating to look over on the right side and kind of see where you're hoping to get to. All right? Play the recording when you're ready. Okay, so if we work this out, I'll just take those first two. Okay, so at this point, if you want to use a box here, a 3x2 box, to use an area model, that's cool. I'm just going to multiply this out. I'm going to multiply the a, get a cubed, supposed to be a 3, plus 2a squared b plus a b squared. And now when I multiply the b, I'm going to write that right underneath. So b times a squared is a squared b. So I'll write that underneath here, a squared b. Now b times 2ab is 2ab squared, and b times b squared is b cubed. Okay, so now I can just add these up vertically. So I've got a to the, and that all is equal to what my right side was. All right, so that checks out. And now finally it says, use your calculator to work out 11 cubed. Okay, and then show the identity works. So 11 cubed, you can pump that in your calculator. Turns out it's a nice palindrome of a number, right? 1331. Okay, so what are we going to let a and b equal? So think on that and play the recording when you're ready. Okay, so hopefully you thought about that a little bit. I'm going to let a equal 10 and b equal 1, because I can split up 11 into two numbers that a and b equal, that are easy for me to cube and multiply by 3, etc. So again, I could have split it up anyway. I could do 5 and 6, but I don't know 5 cubed and 6 cubed, and I don't want to work with those numbers as much as I like 10 and 1. So, all right, that's the left side. Then the right side, I'm actually going to need a little more space. Let me move those guys over. So the right side, we're going to expand that all out using the identity, where a is 10 and b is 1. So I've got 10 to the third power, which I know. And then 3 times 10 squared times 1. All of those are easy, right? Plus 3 times 10 times 1 squared. Plus 1 cubed. Everything in there is a piece of cake to work out. So go ahead and simplify that. Show that it works out to be 1,331. And there you have it. Thanks for watching.